This will be the first part of lecture 13, and I'm going to treat the quantum physics of lasers, and in particular as it relates to statistical distributions. So we already found early in the course when we looked at the perturbation theory of light on atoms that we can have a variety of possible effects. There is, when light comes in, we excite, when light has the correct energy, we can excite from an electron from a lower energy state to a higher energy state. That process we call absorption because the photon comes in and is converted into excitation in the electron. We absorb the photon. The second thing that we observed was that if an electron is in an upper state and then light comes into the system, it can stimulate the emission of the electron into a lower energy state. So when the incoming photon energy is correct, we can actually stimulate emission. That process here is labeled as B, as stimulated emission. So these two effects we already found. Okay. Then there's a third effect, which is related to background radiation, actually, and that's called spontaneous emission. That is that the electron spontaneously decays from the upper state down into the lower state, emitting a photon in the process. The absorption and spontaneous emission cross-sections actually have to be related to one another because in thermal equilibrium, we have to have the correct ratio of electrons in the upper state to electrons in the lower state. And the light that gives rise to this excitation is just background radiation or Planck radiation. And the actual spontaneous emission is due to Planck radiation interacting with the electron in the upper state. So first, let's look at this idea that what goes up must go down and write down some rate equations for electrons in these two states. So state 1, state 2. I have a number of atoms with electrons in the lower state and a number of atoms with electrons in the upper state. And we can, using these three effects, figure out what the rate of change of the number of electrons, for example, in the upper state is. So the rate of change of the number of electrons in the upper state is going to be equal to process C, all right, which is absorption of light, taking an electron from the lower state to the upper state, okay, process C, which is going to be related to the flux of photons. So that's what we're going to take U to be the photon flux at a particular frequency F. I haven't labeled F here, but flux of photons at the frequency that induces the transition times the number of electrons that are of atoms that are in the lower state, all right, times this cross section, what's the probability if a photon interacts with an atom that the excitation is going to occur. So first of all, I have to have an atom in the lower state, and I have to have a photon of the correct energy, and then I've got some cross-section for that to happen. So that's what this is. C sub U sub F, I put the F in here, times the number in the lower state, is the rate at which we excite from the lower to the upper. All right. Then we have spontaneous emission, right, and stimulated emission, right? Stimulated emission is related to the flux of photons that are available, and spontaneous emission is just the decay from the upper state to the lower state due to other processes. And in order for the decay to occur, the atom has to be in the upper state. Okay, so I can write a similar rate equation for the lower state, which is the rate at which I excite out of the lower state, plus the rate at which electrons enter the upper state. And in steady state, the rate of change of each of these things is the same. because I have only two levels here, it turns out that these two equations end up yielding the same relationships. But in steady state, the rate of change is 0. Okay? So that means that in steady state, thermal equilibrium, these coefficients, A plus B times the photon flux times the number in the upper state, is equal to C times the photon flux times the number in the lower state. Those two effects, the rate at which it goes up must be equal to the rate at which it goes down. Okay? Now, what we're going to do is assume the two states are sufficiently far apart that we can use a Maxwell-Boltzmann distribution to describe their occupation. And if that's so, then the ratio of the number in the upper state to the number in the lower state must be equal to e to the minus difference in energy between the states over Boltzmann constant times the temperature. So I've just written this in a slightly shorter form here with the frequency specifically in there. And we can combine that. Now we can put that into the relation from the steady state equation that we had before, which had N1 and N2 in it, that those must be in that ratio. We put that in. And this tells us that under thermal equilibrium steady state conditions, the density of photons is related to the coefficients A, B, and C in this way. And we compare this to the actual Planck distribution, which we know is what we should have in a box, for example, which has got some atoms in it. Then that tells us that C must be equal to B. That is that stimulated emission, stimulated emission rate must be compared to the stimulated absorption cross-section. So those two cross-sections, absorption and stimulated emission, are the same. Okay? And the ratio of A to B in this relationship here, or A to C, right, ends up having a frequency relationship that looks like this. Right? So by this assumption of thermal equilibrium and some simple occupation statistics, as well as basic rate equations, rate up, rate down, we end up with relationships between what the cross sections for various effects must be. So taking those coefficients as we know them, we can plug those in and actually calculate the occupation of the N1 state, the upper state, and the lower state as a function of the photon flux in the problem. All right, so here we're going to actually put the correct A's and B's and C's in and go ahead and calculate as a function of photon energy density. So photon flux. So now we're not talking about thermal equilibrium any longer. We've got a photon flux that we have induced in the system. We, for example, are shining light on the system of a certain frequency, and under that excitation of light, where some fraction of the light has a frequency is just right to make the excitation from state 1 to state 2. Under those conditions, then when the photon flux is very low, almost all of the atoms are in the lower state, very few in the upper state. So I know this looks upside down, but these are the numbers in each of the two states. As we turn our photon flux up, then we begin to get more excitations out of the lower state into the upper state. But when the flux gets high enough, then we actually begin to stimulate emission as well. So we have absorption and emission, and that stimulated emission and absorption processes compete with each other, and we will always have more in the lower state than in the upper state, but at very high fluxes, they approach one another. The number in the upper state can never be greater than the number in the lower state. So just summarizing here, that the coefficient for B, stimulated emission, is equal to the coefficient for C, which is the absorption process, is consistent with what we did in quantum mechanics earlier in the semester. Perturbation theory told us this. Cross sections are the same. The rate of stimulated emission versus absorption is proportional to the intensity of the light. So if we turn the intensity of the light incident on the system up, we can make stimulated emission and absorption dominate the transitions, and we can ignore the spontaneous effect. But even under those conditions, the best that we can do is to make N2 nearly equal to N1, but always less. And as long as N1 is greater than N2, then when we shine light into the system, the rate of absorption, loss of photons in the system, has to exceed the rate of stimulated emission. So we can't make a system that operates with stimulated emission just using two levels in this way. We need actual population inversion, where N2, the number of atoms in the upper state, is greater than N1, the number of atoms in the lower state, in order to make the system amplify incident light. There is a process called superluminescence, where if we actually have more atoms in the upper state than in the lower state, then when a photon comes into that system of the right energy, it can stimulate emission. Then when that occurs, two photons come out. They actually come out parallel to one another in one macro state, but two photons come out. Each of those photons can stimulate more emission and stimulate more and stimulate more. And in the end, we get many more photons out than we started with because we have stimulated emission in each of these cases. One of the things that we didn't actually prove when we did the perturbation theory analysis was that that photon that comes out is actually in the same state as the photon that came in. And so we end up in this situation here with one photon coming in some particular phase and motion relationship. And when the emission occurs, we end up with a second photon, which is exactly in phase and indistinguishable from the first photon, except now that we've got two, and they are bunched together. So in a system like this, if we have all our atoms prepared, then when we stimulate at one end with a photon, and the right thing occurs, the transition occurs, then we can get a blast of photons out the other side. Okay. In many lasers, that's something that we want to do. In steady state lasers, or CW lasers, continuous wave lasers, we don't want one photon in and a blast, so we have to find a way to organize this in order to get a steady flow of photons out of the system. One way to do that is to put mirrors in the system. And we make the system quite long, and then stimulate the system so that we have population inversion. So atoms are throughout this structure here, right? We create a situation with population inversion, and then we, let's say, seed the process by putting a photon into the system. Usually that happens by spontaneous emission. And photons which are traveling along the axis are going to be amplified, and photons which travel off the axis are not going to be amplified. So I end up with more photons along the axis. And the more photons I have traveling along the axis, the more they dominate the interactions, and they actually steal photons or excitations out of the system that would have led to photons leaving. They all end up traveling parallel to one another, as long as I have a set of mirrors on the two ends that actually reflect most of the light that's traveling along the axis back upon itself. There's one more trick, in that what we want to do is to make the distance between the mirrors just right so that photons that are traveling this way and photons that have traveled the length, gone back and come back like so, are in phase with one another, though they are fully coherent. If we do that, then we get a maximum of intensity inside the system. And then normally what we do is make one of the mirrors only 99% reflective so that 1% of the light gets out. So the actual intensity inside of the cavity of the laser is extremely high. It's 99 times higher, 99 times higher than the intensity of the light outside of the laser system. In order to actually achieve population inversion, we set up a system that has more than 2 levels. Remember, with 2 levels, we can't get inversion. So what we might do, an example of a simple system that corresponds to a real system, is that we've got our ground state in the system and we have 2 excited states. The upper excited state decays very rapidly from that state. An atom in this state decays rapidly to this state. So we excite to here, then we have a very rapid decay from this upper state to the lower state, okay? And then if this has a long lifetime, E2 has got a long lifetime for this transition, then we can end up by pumping from here to here and then emptying that state rapidly. We always have an empty spot for an excitation to go to. We can achieve inversion, more electrons in state E2 than we have in E1. Once we have inversion, then we can get stimulated emission, amplification by stimulated emission. A better example, a better laser system actually is set up so that we pump from the ground state to a short-lived upper state, just as we had before. And then there's a rapid excitation into state E3, okay? And a slow decay from E3 to E2, which means that we can achieve inversion, and therefore stimulated emission will be dominant here. And then we want to keep state E2 as empty as possible so that we get maximum inversion. Lots of electrons here, or lots of atoms here, very few in this state. And a way to do that is to have this lower state decay very rapidly into state E1 down below. So if we're decaying rapidly here, we might have a fairly high occupation in E1. We'll have a very low occupation in E2. So stimulated absorption is quite easily done here. And then the process of short lifetime, long lifetime, short lifetime achieves inversion here. And we don't have to worry then about what the occupation of the ground state actually is. So it turns out that this is a more efficient system.